There is a dark side to our universe. Most of the cosmos is made of something astronomers cannot see at all. Dark matter.
We're going to be designing an experiment to look for the annihilation spectrum resulting from dark matter collisions in space.
Ooh, dark matter. We better bring a flashlight.
Welcome to OMNIA, the podcast on all things Penn Arts and Sciences. In our new series, OMNIA 101, we talk to faculty members about integral aspects of their research, shedding light on their biggest challenges and their strategies for conquering them. Mark Trodden, chair of the Department of Physics and Astronomy and the Fay R and Eugene L. Langberg Professor of Physics, and Masao Sako, associate professor and undergraduate department chair, have different approaches to exploring two of the greatest mysteries in their field, dark matter and dark energy. Trodden, a theoretical physicist, devises mathematical models in an effort to explain the cosmic data that observational astronomers like Sako obtain using telescopes and other tools. We asked both of them to help us understand dark matter and dark energy, beginning with Professor Sako.
So, embarrassingly, we know very little about the physical nature of dark matter and dark energy. We think we know how much of those exist in the universe. So, for example, dark matter is believed to make up about 85% of all of the matter in the universe. And we have absolutely no idea what it is. We know it's there because of its gravitational effects on the stuff around it, and we can measure the properties of it. But again, we have no idea what it is. There are many candidates. They could be mysterious particles that we've never seen, something that may have been produced after the Big Bang, for whatever reason doesn't interact with us, normal baryonic matter. There could also be a place in parameter space where Einstein's gravity maybe actually fails. And so our theory of our understanding of gravity may not be complete. Some people don't think that's possible because Einstein has not made any major mistakes so far. We're still doing his homework and checking off everything that he's predicted. As an observer, it's embarrassing that we, after decades of taking data and trying to detect or measure what it is, we have no idea what it is.
Really, you're inferring the existence of something from the behavior of other things. I mean, if I were to roll steel bearings along this table, I would release them at one end and you would just watch them roll in straight lines. That's what you would expect. Now, if they were not rolling in straight lines, if they started moving around, you might suspect that there was something else going on. And maybe I've got a magnet under the table. You don't see that magnet, but you would infer within rolling enough balls that there was something there. And you would also infer its properties, the size of the force it exerts, etc., the range of the force it exerts. So in some sense, that's the kind of thing we're doing with dark matter.
Professor Trodden, who co-directs Penn's Center for Particle Cosmology, discusses the difference between dark matter and dark energy.
So on the other end of the scales is dark energy. You know, dark energy is a very different thing. It discovered a little over 20 years ago. You know, or at least you will have heard that the universe is expanding, and that means that faraway galaxies, very faraway galaxies, are moving away from us. And that's fine. That's something we've learned to accept and understand and interpret within the context of our theories of gravity and matter. But one thing you also know is that gravity is an attractive force. You jump up off the surface of the Earth, you are attracted back to the Earth. You don't accelerate away from the surface of the Earth. So even though the universe is expanding, things are moving away from us. You would expect in any normal understanding of gravity that those things that are moving away from us would be slowing down because, after all, they're attracted to everything else in the universe. And a remarkable discovery of 20 years or so ago is that is not happening. In recent years, where recent here means in the measure of billions of years, distant things have started to speed up in how they move away from us. And that is contrary to almost everything we understand about the way gravity and indeed matter works. And it's a complete mystery. And we know that whatever causes that should not be some particle sitting around there like dark matter would be. It has to be something much more mysterious. And we know that it's better described not really as matter. And so we don't see it because it doesn't glow. And so we call it dark energy. And that is also something we don't understand. And in some ways, a much more deep problem than the problem of dark matter. I'm going to take issue with something Masao said earlier. He says it's embarrassing as an observer that they don't know that. I think it's quite the opposite. It's theorists, I think, that are the ones that are stumped here. In the last sort of, I would say, 20 years or so, and it's going to continue, I think, for decades to come, have been a golden time for observational cosmology, people like Masao and his colleagues. And they have made great strides, both technologically and scientifically, in how we probe the universe. And they have revealed to us the details of dark matter's behavior, the existence of dark energy, its features. And they're going to continue doing that to greater precision and presumably turning up new surprises for us. So I don't think there's a lot of embarrassment there for observers. I think the embarrassment is for theorists who are still struggling to explain these phenomena and interpret them in terms of our theories of fundamental physics. But it's also a fantastic challenge for us. So, Masao is, he's the best person to tell you how they actually go about observing these things. But, people like me are supposed to figure out, what is dark energy? Okay, you're giving us all this fantastic data. What's it made of? And that's very exciting from the point of view of people who are trying to push back the frontiers of what we understand about fundamental particles, space and time, et cetera, et cetera.
Professor Sako is one of the leading researchers on the Dark Energy Survey, a 6-year project probing the universe's expansion. He explains that dark matter and dark energy can be explored using Type 1a supernova explosions. These explosions happen when certain types of stars die, emitting varying levels of brightness that give us information about the universe.
So the discovery of dark energy was made back in 1998 by using things called Type 1a supernova explosions. So there's a certain class of stellar explosions that are all roughly the same luminosity. They emit the same number of watts of energy per second. You can use those to measure distances to those explosions by measuring how bright they appear to us. And so if you do that at many different distances, it gives us a way of mapping out the expansion history of the universe between now and then. And the expansion history of the universe tells us how much dark matter and dark energy there exists. So what we're doing in the Dark Energy Survey is we're identifying thousands of new Type 1a supernova explosions that we found and we measure the properties of. And for every single one, we're trying to make the best measurements of the distances to them, literally in centimeters, to the distances to each of the supernova. And that gives us a very good idea of the expansion history between now and the farthest supernova that we found, which is more than 2/3 of the way back to the Big Bang. And that's going to tell us how much dark matter, how much dark energy there exists, and even try to put constraints on the possible evolution of the properties of dark energy, which is an important thing. If it doesn't evolve with time, it could be this cosmological constant, which is a number. And if it's just a cosmological constant, we'll measure that number, and that's the end of the story. But if it does evolve with time, then that is a huge discovery. And we're hoping that with thousands of new Type 1a supernova explosions that we found, we can actually put constraints and maybe measure deviations from a cosmological constant.
Albert Einstein's theory of general relativity serves as a foundation for our understanding of the universe. But, as Trodden explains, the discovery of dark energy has called some of his ideas into question.
When you see something that you don't expect, there are a couple of possibilities, right? One is there's new stuff that's causing that. The other possibility is there's not new stuff, but the rules that you thought associated the matter of the universe with the way in which space and time behaves are not quite what you thought they were. In other words, perhaps Einstein's description of gravity is slightly modified. So that's a very radical idea. It's something many of the theorists here at Penn have played a central role in exploring, both sort of connecting it to the data, but also exploring its deep mathematical implications and whether it makes sense as a theoretical proposal. And I'm hopeful that the kinds of experiments and observations that Masao and his colleagues are going to do in the coming decades are going to give us a handle on that question. And that will blow open theoretical physics, the answer to that question. And so I'm very excited about that. The other thing that I'm excited about is at the other end of time. Dark energy is something we notice today. At the very earliest times in the universe, that's another area of extreme mystery. And, I talked about you can only view in the early universe. In the earliest times in the universe, anything earlier than about a few 100,000 years after the Big Bang, the universe is so hot that light cannot escape it. So we can have no optical information about that era. And so this is one reason we would really love to use things like gravitational waves as a probe of that era. And if you can measure those, it's going to give us an exquisite handle on the kinds of physics that caused the early universe to behave the way it did today. And what you'll be doing is you'll be looking at the sky today, measuring subtle differences in it and the way its radiation behaves and the way its structure behaves, and inferring something about not just 100,000 years after the Big Bang. Bear in mind the universe is 14 billion years old. Not just 100,000 years after the Big Bang, but earlier than a tenth of a nanosecond after the Big Bang. Ridiculously early times. And that, the energies of the universe were extremely high then, much higher than we can make in colliders on Earth. And so that's a direct window into the fundamental workings of matter, light, energy, space, and time. And for people like me, that's everything we could ever hope for. So that's something I'm very excited about.
I was a graduate student in 1998 when the discovery of dark energy came out. And I was working on something completely different. I was an X-ray astronomer. I was studying X-rays emitted around black holes, which has nothing to do with dark energy. And I heard about these results, and I said, okay, kind of cool. Maybe true, maybe not. But then, as the years went by, people were confirming, they were making better measurements and confirming the existence of dark energy and dark matter. And then there was, I think there was actually a time when I said, what is this 85% of the matter that we're not seeing? Why would nature do that to us, hide all of these, stuff from us and make it invisible? And since then, I'm more interested phenomenologically in dark matter than dark energy. Dark energy, I think, is too complicated. I'm not expecting to understand what dark energy is in my lifetime. But I'm really hoping that I would, before I die, know what dark matter is. It's just something that has to be explained, and we need to figure it out.
One of the great things I find about being at Penn and working in this environment is that people like me, I don't spend my time with this data the way Masao does, but to have Masao, people like Masao 2 doors down the corridor is great. The most cutting edge work that's going on in this field right now is happening in surveys in cosmology, of which Penn is playing an integral part, and Masao himself is an integral part of that. So the fact that our theorists are also here, this is sort of the reason we have this thing we call the Center for Particle Cosmology, is precisely to bring together theorists like me and my colleagues like Bhuvnesh Jain and Justin Curry, together with people like Masao and Mark Devlin and other people up here, Mariangela Bernardi, people like that, in order to be able to sort of discuss the implications of this data and try to understand the constraints it places on theoretical ideas, and also how hints in it might lead us in the right direction to develop some new ideas.
I don't think anyone should particularly care about dark matter and dark energy, but the basic science that we do should not be about helping your immediate needs. Right? You need to push your boundaries and try to understand everything around you in every way possible. If we stop doing that, we're not going to make advances in technology or in humanity. So I think it's our responsibility to try to understand the universe and everything around us.
We explore things. That's what we do as humans. We didn't go to the moon in the vague hopes that there would be gold there. We went to the moon because we thought it'd be fascinating. And so you do it because you want to know how the world works. Why are things the way they are? How does it work? Not just why does the Earth go around the sun, or in fact, historically, does it go around the sun? But why does the solar system go around the galaxy? What are those things in the sky? What are they made of? Are they made of the same things of us? Historically, people have thought this is really worth doing, and I hope they continue to do so.
This has been a presentation of Penn Arts and Sciences. Special thanks to Professors Mark Trodden and Masao Sako from the Department of Physics and Astronomy. To listen to previous episodes of the OMNIA podcast, visit our website or subscribe to the OMNIA podcast by Penn Arts and Sciences on iTunes.